Alright, are we here? Can people hear me? I have no idea. I can't hear me. That's okay though. We have 0 viewers! Lovely. Very happy to see that. I hate people. Alright, I look like a condom, and that's a very good thing. Okay, let's see if I can remember how to pop out the chat. Wow, that was the quickest I've ever done it. I'm proud of myself. I've not done anything that cool this day, sadly, so this makes me happy, slightly. Here we are, we have 1 person joining in. That's me, I assume. I don't know how Twitch works. If you guys haven't noticed yet, I'm a little bit of an idiot. Tiny bit of an idiot. I'm hoping Keith joins in because I lost his Mastodon. I'm an idiot. I'm just gonna wait here for a bit. I'm gonna ramble about... I don't know what I'm rambling about. I'm just gonna turn my video capture device off for a moment because I'm gonna drink some tea. I'm a weirdo. I drink tea. It's cardamom tea. I don't know what that is. I'll be clear. Nothing what cardamom tea is. Alright, looks like I kinda lied. We're gonna go through the recap of this and finally get the fuck out of ownership. We've been in ownership for 3 days. 3 days of ownership. We'll finally get into structs. I like structs, dude. They make sense. I'll admit, I don't fully understand the difference between a struct and an enum. It's kind of embarrassing, to be honest. Should likely have quit out of this stuff earlier. Right, just gonna wait a little bit. People may pop in, people may not. Either way, I'm gonna read through this. I mean, if I'm alone, that's a shame, but you know, what are you gonna do? Sometimes you're just alone in life. You gotta understand that. What in the world is this or .rust? That's in the previous thing. Well, it's gone now. Yes. I've been thinking of making a command line file browser. I hate the current ones. Ranger's cool, I quite like it, but I like that weird like bar that goes on the side for like downloads and documents, music, stuff like that. None of them have that. I understand it's not really useful, but it makes me comfortable to see it. It's saddening. Alright, I'm just gonna wait a little bit and then I'm gonna start reading. I did not put this up very quickly, so got 4 upvotes on. I don't really think. I am nearly certain that there are quite a few bots on Lemmy. Seriously. everything I post gets a lot of upvotes, but not a lot of downvotes. I mean, quite a lot relative to Lemmy. It's a very small collection of people. To be clear, I'm just gonna wait until exactly 7:40. So skip to 10 minutes in if you so wish. If you're watching the VOD. You think by now I'd know what the fuck to say during a lull. I don't. I'm just kind of filling space. I don't think I need this open, to be honest. At the very least, what I'm doing here is forcing myself to read this every week. I haven't gotten this far at any point in my reading. Finally, we start talking about ownership versus garbage collection. We had, I believe Keith brought up that it sounded a lot like garbage collection. I'm glad that they get to speak about how it isn't garbage collection. Well, it isn't a garbage collector, I guess. Oh, hey, Keith! Keith! I need your Mastodon. I missed it. I thought I copied it, but I guess I didn't correctly, and it just kind of went into the Aether. I have no idea where it is. Glad to see you, Keith. I'm just waiting a moment, drinking some tea while I wait to see if anybody else joins in. Ah, Universidon. I looked at that one. I'm just on social. I made an account literally today. I'm gonna message you right now, if I can. I'll admit, not much of a Mastodon kind of guy. It was never for Twitter or anything. Well, it was a reasonable thing. How the... How do I even do this? How do I do anything? Private mentions. I'm just gonna search you up. I found you. I'm now following you. God damn, you got a nice following, man. You're a bit famous. Just in newsfeed? Pretty decent. I'm at least following you. No idea how to message. Privately mention. How does... I don't know how any of this works. Like, I'm a web programmer, but I have no idea. Yes! Honestly, you're more famous than I am. You're a god amongst us, man. You're a god amongst us. I got 13 followers. You're at least 4 times the man that I am. I have 2 notifications. Hello! Is this a private message? I don't know. I'm gonna publicly tweet this to everybody. Or shoot this to everybody. Okay. Thank you for that. Alright, so I am going to start this quite early on. I'll message you tomorrow or after this about talking to you in private about just recapping some stuff. It would be good for me to go through what we've learned and see if I actually know it or if I'm just delusional. which happens a lot, to be honest. I really do appreciate the opportunity if you're alright with talking to me at a later date. That is a noise. Great to hear. Maybe I can leech off of you, man. Alright, let's try and get the camera back up. I believe that'll work. Having some issues. I'm on a weird system right now. When am I not? Hopefully that didn't make a horrible noise. Alright, so I am just going to start reading right now. Welcome back, I guess. This will be the final ownership session. It's been 3 sessions in a row. 3 separate sessions we have been reading about ownership. Honestly, I think this section of the book has started to own me. Anyway, let's start reading. Ownership recap. This chapter introduced a lot of new concepts like ownership, borrowing, and slices. If you aren't familiar with systems programming, this chapter also introduced new concepts like memory allocation, the stack versus the heap, not very well explained, pointers, and undefined behavior. Before we move on to the rest of Rust, let's first stop and take a breath. We'll review and practice with the key concepts from this chapter. Ownership versus garbage collection. To put ownership into context, we should talk about garbage collection. Most programming languages use a garbage collector to manage memory, such as in Python, JavaScript, Java, and Go. A garbage collector works at runtime adjacent to the running program. A tracing collector, at least. The collector scans through memory to find data that is no longer used. That is, the running program can no longer reach that data from a functional That is, the data can no longer reach that data from a function local variable. Then, the collector deallocates the unused memory for later use. Key benefit of a garbage collector is that it avoids undefined behavior, such as using freed memory, as can happen with C or C++. Garbage collection also avoids the need for complex tape systems to check for undefined behavior. Type, not tape. Garbage collection also avoids the need for a complex type system to check for undefined behavior. I don't know why I just said type, tape, and was okay with it. I was going to ask about that, but I just said it. Like in Rust, however, there are a few drawbacks to garbage collection. One obvious drawback is for performance, as garbage collection incurs frequent small overheads for reference counting, like in Python and Swift, or infrequent large overheads for tracing, like in all other GC languages. GNU compiled or garbage collector? I don't know why I thought GNU compiler. But another less obvious drawback is that garbage collection can be unpredictable. To illustrate that point, say we are implementing a document type that represents a mutable list of words. We could implement document in a garbage collected language such as Python this way. We have a class called a document with a definition of __init. So we define the function of init, which takes in self words, which is a list of strings. Creating a new document, self.words equals words. We add words, we got self.words.append words, and get words, which takes in self, and returns self.word. It's a list of all the words in the document. Here's one way we could use this document that creates a document D, copies it into a new document D2, then mutates D2. Words equals hello. D equals document word. D2 equals document D.getWord. D2.add word. World. Okay, so we have D, which equals a document word, and then d2, which equals the words of d plus this new word. Consider two key questions about this example. When is the words array deallocated? This program has created 3 pointers to the same array. The variable word d2 all contain a pointer to the words array allocated on the heap. Therefore, Python will only deallocate the words array when all 3 variables are out of scope. More generally, it's often difficult to predict where data will be garbage collected just by reading the source code. Most people in Python just don't think about it. They don't care, which is why Python code tends to run pretty terribly if you have it on a massive project. The thing is, this also takes into account the fact that people tend not to care about it running poorly because we have these massive computers that are just way too powerful. Not something people tend to care about. What are the contents of the document D? Because D2 contains a pointer to the same words array as D, then D2.add_word world also mutates the document D. Therefore, in this example, the words in D are hello and world. This happens because D.getWords returns a mutable reference to the words array in D. Pervasive, implicit mutable references Pervasive implicit mutable references can easily lead to unpredictable bugs when data structures can leak their internals. Here, it is probably not intended behavior that a change to D2 can change D. That's what I would assume too in Python. I would assume that D2 is an entirely new thing. This problem is not unique to Python. You can encounter similar behavior in C#, Java, JavaScript, and so on. In fact, most programming languages actually have a concept of pointers. It's just a question of how the language exposes pointers to the programmer. Usually it's through just saying pass by reference versus value, which is why I've been saying that so often. It's just a question of grammar. Garbage collection makes it difficult to see which variable points to which data. Correct. For example, it wasn't obvious that D.getWords produced a pointer to data within D. By contrast, Rust's ownership model puts pointers front and center. We can see that by translating the document type into Rust data structure, Normally, we would use a struct, but we haven't covered those yet, so we'll just use a type alias. Type document equals a vector, which is a vector of strings. You have new document, which returns document, and just outputs words, whatever you put in. That's useless. That's useless. Function addWord is just, this is something you put in. I'm sorry, don't do that. This is a mutable reference to a document, and it also takes in word. This.push word. We just add in word to this. This.addSlice returns it. So we just return a reference to an array of strings, I believe. The Rust API differs from Python. Alright, let's see how this changes anything. Right, yeah, it's just telling you exactly what's being posted. It tells you exactly what's being returned. And exactly what's mutable and what's a reference, and at all times you understand what's being done. Because it's explicit. You need to explicitly state that it's mutable. You need to explicitly state that it's a reference. Makes sense. REST API differs from the Python API in a few key ways. The function new_document consumes ownership of the input vector words. This means the document owns the word vector. The word vector will be predictably deallocated when its owning document goes out of scope. There. The document addWord requires a mutable reference mute document to be able to mutate a document. It also consumes ownership of the input word, meaning that no one else can mutate the individual words of this document, which is better than C. The function get_words returns an explicit immutable reference to strings within the document. The only way to create a new document from this word vector is to deep copy its contents like this. We have word, which is a vector, containing hello. This would be a reference str or a slice originally. Now it's turning it into a full-on string. Let d equal new_document words. We have d, which equals hello, a vector, one word. .tvec converts equal get_words, reference d, which just posts out all the words, meaning hello. And then we change it to a vector. Yep, by cloning each string. Let d2 equal document_new_document word copy. So now we have two documents which have the same stuff in it, but actually, hello. I think things messed up for a moment there. Am I back? Just gonna refresh. Hello, I believe that I'm back. Sorry, I think I cut out for a moment there. I don't know if I'm fully back though. I would love for somebody to sound off in chat if I am. You still might not be back yourself. Makes sense. Perfectly reasonable. The audio has been cutting a bit. Ah, shit. Sorry about that. I might be able to fix that. That may just be a network issue. No. It's going to take a moment. My god, is this ever delayed? Seriously, this is like 40 seconds? I'm watching myself do things I did a while ago and waiting for my response. Okay. The audio has cut and back a few times. Not sure if your connection or mine. Yeah, I think it might be my connection. It's probably my connection. I've been having a really shitty connection for the past, like, I don't know, 7-8 hours. That's what you get for living in literally the middle of nowhere. Yeah. Okay, that should be a little better. I'm going to keep my audio feedback currently running. It's going to mess up how I speak a bit, but it's going to let me see if there's any issue a lot quicker, because again, there is a massive delay. This entire sentence from the original point of view just came in. It's still actually not in. I'm just going to keep talking until eventually I can hear myself say the words, which I literally have just said. Holy shit, this is taking... No, I just said that should be a little better. Wow. Holy shit. There we go. I just started talking. Okay. Right, now where were we? God, I gotta start cutting down this content and posting it on a separate release schedule. Right. Sorry about that, Keith, and the second person watching, though I think that also might be me. I believe there's two me's in this. The point of this example is to say, if Rust is not your first language, then you already have experience working with memory and pointers. Rust just makes those concepts explicit. This has the dual benefit of 1. Improving runtime performance by avoiding garbage collection, and 2. Improving predictability by preventing accidental leaks of data. Sorry, I probably should have asked if we need to go back a bit because of the cutting out audio. That would be perfectly reasonable. I'm just going to wait the requisite 20 to 40 seconds for the screen to catch up. I see myself talking. This is incredibly weird. I hate that. Luckily, I'm wearing a mask, so it isn't my ugly face I have to stare at. I think I'm saying it now. Alright, we're good. Fantastic here. Let's continue. The point of this example is to say if Rust is not... if Rust ain't your first language, you've already used pointers, but they didn't tell you. They were lying to you. The fiction. The concept of ownership. Next, let's review the concepts of ownership. This review will be quick. The goal is to remind you of the relevant concepts. If you realize you forgot or didn't understand a concept, then we will link you to the relevant chapters which you can review. Ownership at runtime. We'll start by reviewing how Rust uses memory at runtime. Rust allocates local variables in stack frames, which are allocated when a function is called and deallocated when the call ends. So while you are within a function, it is alive. Another num, stack, ref, etc. exists only until this point ends. After inner, it's dead, gone. Local variables can hold either data, like numbers, boolean, tuples, or a pointer, or pointers. Pointers can be created through boxes, pointers owning data on the heap, or references, non-owning pointers. This diagram illustrates how each concept looks at runtime. We have main with mutable a num, then we call inner. Location 1 states, hey, we own all this stuff. Another num, a stack ref, a box stack ref, a box heap ref, etc. All this stuff is owned within inner at location 1 at the end here. All of this is pointing to the number 2, quite useful. At location 2, at the end of inner, it all dies, is gone. And all that exists is a underscore num. It only exists as the function exists. Once it's over, it's over. That's stack memory. Also, the heap memory is gone because nothing is utilizing it. Review this diagram and make sure you understand each part. For example, you should be able to answer, why does a box stack ref point to the stack while a box heap ref point to the heap? That's a good question. A box stack ref is a pointer to a box that is just in heap memory. In stack memory. So a box is a pointer, as you see here, to heap memory. This is a pointer to a box, which is just a pointer here. So we are just pointing in stack memory. A pointer usually is in stack memory if it's utilized in this way. You're pointing to a pointer that is also in stack memory. This is not a heap reference because the 2 is what's on the heap inside of this box. In order to be on the heap in this situation, we are utilizing a box. So, the reason why a stack ref is inside the stack is due to the fact that it's pointing from the stack to a pointer in the stack already. A box heap ref takes I want a reference to what a box points to. A box points to the heap. They want a reference, the dereferencing of a box. So they go to a box, hey, let's dereference that. It is referencing 2, but we want to point to that 2. We want a reference to that 2. So, we get it. We ask for reference, and it points to heap memory. That's why a box heap ref points to the heap, and a box stack ref points to the stack. Why is the value 2 no longer on the heap at location 2? Well, because there's nothing that references it. Nothing that owns it, nothing that references it, nothing has read, write, or ownership permission. It's unused, and thus is dead. It's unaccessible memory, and thus it must die. Why does a_num have the value 5 at location 2? That's a good question. Oh yeah, we pass a mutable reference to a_num into here. I didn't actually read what it does. Then we take where do we use this? Where do we use x? Where do we use x? Yeah, x plus equals 5. We take a dereferencing to x. So we say, hey, we want the value, and then we plus equal 5. The value of x plus 5. That's why it equals 5. Because we added 5 to at the end. And this is a mutable reference to it. So we are taking a num, the physical thing, and we are handing it over to inner. And then at the end, ownership returns back into main, and we can utilize it after this point, I believe. Either way, a_num will equal 5 because we added 5 to it inside of inner. If you want to review boxes, read chapter 4.1. If you want to review references, reread chapter 4.2. If you want to see case studies involving boxes and references, reread chapter 4.3. I'm glad this exists because somebody could very reasonably not understand certain concepts. Here are lists on what to read in that case. Slices are a special type of reference that refer to a contiguous sequence of data in memory. This diagram illustrates how a slice refers to a subsequence of characters in a string. Let S equal string from ABCDEFG. Let S_slice equal reference S 2 to 5. That would equal B, C, D, E, F. Note 1. That would equal C, D, E. I'm a bit of a fool. Yeah. 0, 1, 2, 3, 4, 5. Isn't that inclusive? Why is F not there? Is that because of my... I don't know why that's... Maybe I should reread chapter 4.4, because obviously I don't fully understand it. I thought that was an inclusive range. Ah, well, whatever. Rust tracks read, write, and own permissions on each variable. Rust requires that a variable has appropriate permissions to perform a given operation. As a basic example, if a variable is not declared as letMute, then it is missing the write permission and cannot be mutated. Let n equals 0, we have read and ownership, but not write. Won't work, that'll fail. Does not have write, but has read. A variable's permissions can be changed if it is moved or borrowed. A move of a variable with a non-copyable type, like box or string, requires the read and ownership permission. And the remove eliminates all permissions on the variable. That rule prevents the use of moved variables. Right, we have a string from hello world, consume a string, passing it to a function. I kind of like it. It's kind of funny. Hey, very professional. Nom nom. Print line. We just print S. You can't read it. That will fail. Thus the questioning crab. Judging us. If you want to review how moves work, reread chapter 4.1. Borrowing a variable, creating a reference to it, temporarily removes some of the variable's permission.
Immutable borrow creates an immutable reference and also disables the borrowed data from being mutated or moved. For example, printing an immutable reference is okay. Let mute s equal string : from hello. We have a reference, so we have immutable s. Sorry. Yep. So we have s underscore ref is just a reference to s. We remove right and ownership from s because we currently have it here. We have read and ownership, meaning we can't change this. Well, this is in use. Print line s underscore ref. We print the value under the ref, at which point it is no longer used, so the read and ownership are deleted, and the read from the dereferencing is also removed. But s regains right and ownership because s underscore ref is no longer in use. So we can use it. We can also change it if we so wish. At the end of it, when there are no more references, it loses all permissions. But mutating an immutable reference is not okay. So s equals string from hello, s underscore ref equals reference s. It gains read, but not write, nor ownership. The dereference gains read, meaning we can read the value, but we can't write from it. We can't write to it, we can't change it, and we don't own it from that position. S underscore ref dot push string world print s. That fails because we can't actually write to it. Don't got the permissions, don't got the permits. And mutating the immutably borrowed data is not okay. Let mute s equal string from hello. Apologies. Right, yep. So we got string called sref. This is right and ownership because it's not a mutable reference. Try and push world to the string. Isn't that literally the same thing? And mutating an immutably borrowed data is not okay, but mutating an immutable reference is not okay. This is the same thing. That's the same thing. No. I see the thing. We're trying to mutate s, which is mutable, but while this reference exists, we cannot change s because we still have s underscore ref in usage. If we changed s before it was read, we wouldn't know what s underscore ref could be. It could be hello, or it could be hello world. So we don't want to be able to change s while s underscore ref exists. And moving data out of the reference is not okay. Let mutable s equal string from hello. S underscore ref is a reference to s. Gains read within this. We got read on the dereference. Let s2 equal the dereference of s underscore ref. The error here will be that the string does not have the copy implementation. A mutable borrow creates a mutable reference, which disables the borrowed data from being read, written, or removed. For example, mutating a mutable reference is okay. Right, let mutable s equal string from hello. S underscore ref equals a mutable reference to s. We then push the string world. So yeah, if we want to mutate it within a reference, if we want s underscore ref to be able to change it, we have to explicitly state, hey, you can change this. You are allowed to change this. At which point, we can't point it to a new thing. We can't say, hey, point it to this entirely different string. But we are allowed to say, hey, change the string itself. Because we told it we could. But we can't change s. We can only change s underscore ref, or the dereferencing of s underscore ref. Good stuff. And we'll see, hey, that works fine. We ain't got no confused crowd. But accessing the mutably borrowed data is not okay. We have s, which is string from hello. S underscore ref is immutable s, and we want to print s here. Can't read it. Nope, doesn't got read permission. Can't read it. S underscore ref push string world. Well, actually, we could if we didn't use s underscore ref below it. I'm glad that they always do that. If you want to read more about permissions, read 4.2. Connecting ownership between compile time and runtime. Rust permissions are designed to prevent undefined behavior. For example, one kind of undefined behavior is a use after free, where freed memory is read or written. Where freed memory is read or written. Immutable borrows remove the write permission to avoid use after free, like in this case. Right, doesn't work, confused crowd. We have v is a vector of 1, 2, 3. Let n equal a reference to the first section of that vector. v.push 4, we add something out, now we print line. It'll fail here, because we have a reference n. Well, we can't because n has ownership, by my understanding. But also, if this were to compile and work correctly, v would no longer exist, because we have to add one in, which destroys the vector, creates a new vector with a capacity of 4. Alright, now location 1, we have v, which points to 1, 2, 3, and n, which points to 1, 2, 3. Let's click this. Yep, a vector is a pretty big thing. L2, when we try and push, v.push 4, we try and push, n is dead, cannot use it, because because v is destroyed and created. So 1, 2, 3, 4 is in the heap now. Different thing. N points to nothing, which I guess is fine. Undefined behavior. Pointer is used after its pointee is freed. So, since n was freed, since we had to destroy the original data it pointed to in order to create the new vector, n no longer points to something that we own. It points to just some random memory, some random junk. Can't do that. That is a use after free error. Another kind of undefined behavior is a double free, where memory is freed twice. Dereferences of references to non-copyable data do not have the ownership permission to avoid double frees, like in this case. V equals a vector of 1, 2, 3. Vref equals the ref of type reference to a vector I32 equals reference V. Hey, Silver Sorbet! Glad to see you. Sorry you couldn't join a bit earlier. We are currently just going over a recap. So if you've been following along, no real need to worry. Oh no, why did I move? Oh no. Oh. But really, it doesn't really matter. If you've been following along, it's just going over, recapping. Of course, always good to recap, but you haven't really missed anything big today. Right, where were we? Anyway, very glad to see you, Silver Sorbet. We were missing you. Right. Oh, right here, right at the end. If you want to review undefined behavior, reread chapter 4.1 and 4.3. As we introduce, the rest of ownership, as we introduce additional features like structs, enums, and traits, those features will have specific interactions with ownership. This chapter provides the essential foundation for understanding those interactions. Concepts of memory, pointers, and undefined behavior and permissions will help us talk about the more advanced parts of Rust in future chapters. And don't forget to take the quizzes if you want to check your understanding. The latency is way better. That is good to hear. It's been pretty terrible today, I thought, but I guess I'm not really from the viewer's perspective a lot of the time. Right. I guess we should start with the recap quiz to prove to you guys completely I don't know what I'm talking about. Say you're writing a function with the following specs. Roundall takes as input a list of floating point numbers and rounds each number in place to the nearest integer. Which of the following is the most appropriate type signature for a function implementing this spec? I'd love to hear you guys' responses. We have a function, roundall, is a v of vectors type f32. Takes an input of a list of floating number and rounds each number in place to the nearest integer. So we want a mutable reference is what we want here, because we want in place. To change this, we want to take in a list of floating points and do something to it. Not returning anything, just destroying the original thing. It's mutating the original thing. That's what in place means, I believe. That's what I would expect it to do. Secondarily, we have a reference to a vector f32, which returns a vector f32, and we just take in a reference. I believe this makes the most sense, because we are mutating the original, which seems to be what they want. If that's not what they want, they should have given me a better business. They should have given me a better... Wow, words are quite difficult when you haven't slept for a very long time. Anyway, yeah, Silver Sorbet agrees. He is the god here, so let's continue. Say you are writing a function with the following specs. Find contains takes an input. As I said, words hard, words difficult. Find contains takes as input a collection of strings and a target substring. It returns a list of all the strings in the collection that contain the target substring. So we're looking to return something, not looking to mutate. Which of the following is the most appropriate? Right, we have find contains haystack, which is a vector of strings, but a collection of strings and a target substring. Needle is a string, returning a vector of strings. We can return a vector, a reference to a... We don't want to return a reference to an array, but that's not a great idea. That would be dead. Or a vector of references to strings. Right. So I believe that we want a reference to a vector of strings. And we do want a string. I believe that's... No. A substring would make sense to be perhaps of type @string, because that is a slice. I believe it stated that we should be using slices in order to allow for a person to put in a literal, like just quote string unquote. So I believe what we'd want would be a reference to a vector of type strings, and the needle to be a reference string or a substring. Sorry, a slice. So I believe that this would make the most sense because it returns a vector, a new vector too. No. I guess not. Huh. Because this takes in an array, a reference array. I really would prefer a vector. Huh. I'm kind of stuck here. Unless anyone has a specific answer or something they'd like to say, I don't really know. This makes the most sense for me, because we want to return a vector of strings. That would make the most sense. A reference to a vector of strings. We want to take in some form of string. I would agree with any of these. But I don't think we want to return a reference to an array. I don't think that's what we want. Huh. I'm kind of stuck here, to be honest. If nothing else, I believe that this makes the most sense out of it all. We take in a reference to a vector of strings, take in a string as reference, and return a vector. It says to return a list, so I think the one that returns a list of the string. This? You're talking number 3. Or at least if lists and arrays are the same thing. Perhaps I am wrong on what this means, because this to me sounds like it's returning a reference to an array. If it's a reference to an array, then we have a function where an array lives, and then we return a reference to something within that function. If it's within that function, then it dies when the function ends. Unless it's in the heap, I guess. I mean, it probably would be. I'm going to go with this, though. I think at the very least it'll be a good learning opportunity, because what I personally would do is not here. Oh, well, I think this one honestly makes the most sense out of these. A collection of strings returns a list of all strings. Right, so I'm going to go with the last one because it takes a collection of strings, which is a reference to an array, something which can be brought in, a needle, which is a slice, which is the best way to do something. It allows literals, and it returns a vector of reference strings. I don't know about that, actually. I don't know about that, actually. What? What? Now I'm back to this one because that's a vector of references to strings. Yes! 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 That's fine. No, it isn't. I don't know what I'm doing. I think that's fine, though. I think that's fine because it'll be a reference. Returns a list of all the strings in the collection that contain the substring. No, this is fine. Because this is a reference to the original strings. And this will return a vector which points to each of the strings that contain the substring, the needle. I think this is correct. I think that's good. Okay, so that explains what this would be. That explains what that would be. So yes, I believe this is the correct answer. Quite a lot to get there, but I believe this is the correct answer. Due to the fact that this is returning a vector of references to strings outside of the function find_context. It takes in a reference to an array of strings, which then returns just references to the original array of strings, where the slice exists. I think that's correct. Question 3. Rust normally disallows multiple mutable accesses to the same array, even when those accesses are disjoint. For example, this function does not compile. It's immutable v equals a vector. Rust normally disallows multiple mutable accesses to the same array. We have a v, which is a vector 0, 1, 2, 3. Let r the tuple of r0 and r1 equal a mutable reference to this slice and a mutable reference to this slice. And we try and add 1 to that would equal 1, and this would equal 3. No. No? No. I'm sorry, due to the delay, I don't really know what you're saying no to. I'm just going to wait for a moment, see if we can figure that out. I'm currently just watching myself explain what I said. This is a massive delay. You don't think it allows it? Don't think it allows what? I do really hate this amount of latency. I really can't see what people are saying. Perhaps we should switch this over to a weekly Discord call. Or something better. I believe Mutter is a free and open source version of Discord. I mean, it helps my pride, but you know. Oh! Perhaps I just spoke wrong. Fair. Alright, so I'm just going to continue. So this will disallow multiple mutable accesses to the same array. So since we have a slice here which is mutable and a slice here which is mutable, that will not compile due to the fact that R0 and R1 can both mutate, can both change this original V. So here we have R0, 0, which will equal this, plus 1, and this, which will equal 3. Now the problem here is that R0, 2, and R1, 0 would equal this number. They'd be the same thing. You could change that. That would be bad. However, the Rust standard library has function slice, split at mute, that does permit this functionality. As long as you're mutable. Yeah, so this stops you from being able to have, like, this being referenced 2 times, which can each change it independently, which can create race conditions. So that's a good thing. Let mutable v equal vec1234, or 0123. V split at mut 2, which will take this point and split into 2 vectors, r0 and r1. This plus equals 1, which would make that 1. This plus equals 1, which would make that 3. Which of the following best describes how it's possible to implement split at mut? I think that it needs to have an unsafe part. Is that what it's talking about? Split at mut uses unsafe code to disable the borrow checker from checking the safety of a mutable reference. I believe that's true. Split at mut calls into C library that can't be analyzed by Rust. Nope. Split at mut uses unsafe code to circumvent the borrow checker with raw pointers. Ooh, maybe. Split at mut is a special compiler primitive that cannot be implemented within the language. That is incorrect. I'm between these two. I think that is the first. It uses unsafe code to disable the borrow checker from checking the safety of a mutable reference. It uses unsafe code to circumvent the borrow checker with raw pointers. Nah, I think that is this one. I think that is the first. I'm just going to go with that. Consider the permissions in the following program. Sorry if you guys are trying to answer. Again, this is just wildly behind, comparably. Which of the following best explains why dereference s_ref does not have the own permission? We have a string, which is a new string. s_ref is a reference to s. Right, dereference s_ref, ownership. Ownership is currently on s_ref. It is not on the dereferencing of s_ref. Ownership permits mutation? No, it does not. Ownership permits reading and reading reference s_ref. That is not correct. Ownership does not permit reading necessarily. Ownership permits moving, and moving out of a reference can cause a double free. I believe that to be correct. It's fine. Glad to hear. Ownership permits borrowing and reborrowing. Reference s_ref and reborrowing s_ref dereference can cause a double free. I believe these two are the most correct. Permits moving and moving outside of. Nah, I believe borrowing is the correct term. Perhaps both? I don't fully understand what the difference between moving and borrowing are, I guess. I'm glad I'm taking this quiz. Unless somebody can describe to me the difference between moving and borrowing, I understand. I don't really fully understand that. Unless someone can explain that to me, I'm just going to say borrowing because I like the word. It has a B in it. B's are safe. I like them. Okay. I have to wait a moment, but I'm just going to click it anyway, even though it hasn't ended, to be entirely honest. What point am I? Nah, I guess I just answered that, so I'm just going to move on. Goodbye. Consider the set of Rust programs that contain no unsafe. I think it's the reborrowing, because you can't borrow something that you don't own. That's a good point. That's a good point. I'm glad that I did select that one. I did it because I fully understood it. That's why. That's why, Silver. Alright. Consider the set of Rust programs that contain no unsafe code. Select each of the following statements that is true about the kinds of programs accepted and rejected by the borrow checker. That is a terribly worded sentence. They need an editor. The borrow checker sometimes accepts programs with undefined behavior. Probably not. The borrow checker always rejects programs with undefined behavior. I mean, it's probably not perfect, but that's probably what they want to say. The borrow checker always accepts programs without undefined behavior. That is incorrect. Several times it is stated that this will not cause undefined behavior, but we're gonna stop it anyway because we can't know. We're not smart enough right now, but eventually we will be, and that time is not now. The borrow checker sometimes rejects programs without undefined behavior. Correct. I believe these are the two correct sections. A, it will always reject programs with undefined behavior. That is the goal. I don't know if they've achieved it, but that is the goal. Secondarily, the borrow checker sometimes rejects programs without undefined behavior. I believe that's true. Sometimes it will in fact do that. Not I believe, I know that to be true. And thus, this is what I'm going to select. Goodbye. Question 6. This function extract is rejected by the borrow checker. Ooh. Imagine the borrow checker did not reject this function. Determine whether there exists an input such that the function would cause undefined behavior if executed on that input. Right, we have a box which is on the heap. It returns an I32. Let B2 of type box I32 equal a dereference of B. And then dereference B2. What? Okay. I don't think you can, because all we're doing is we create a new box I32 equals a dereference to B. So that would equal the value within the heap that the box, which is an I32, equals. So we take like 7, and B2 equals 7. Dereference B2. Return 7. I don't think that this can. Can anybody imagine an input that would cause undefined behavior from this? To be honest, I really don't think that there is any possible undefined behavior from simply dereferencing B, taking the value within the box, and then returning the value from B2. I'm going to wait a moment, because again, where am I right now in the stream? Yeah, we're actually quite close on here, so unless anybody has something to say, which I really don't think there's much to say, I think I'm just going to continue saying that this can't cause undefined behavior. I can't see it. Yeah, this is a strange question. I don't think that there's anything here. I'm just going to submit this query. Thank you, Silver. The function transfer underscore string is rejected by the borrow checker. Get first, get second, transfer string. Imagine that the borrow checker didn't reject it. Determine whether there exists an input where the function would cause undefined behavior. Right. So we have transfer strings is the thing that is rejected. We take in strings, which is a mutable reference to a tuple with 2 strings in it. Okay. Right, so let first equal get first. And then we put in string. Get first strings takes in the tuple, outputs a mutable reference to strings. Where does this fail? Right. We then return a mutable reference to the first object. Okay, first would equal a mutable reference to this. Second, of course, does the same thing, and it's here. The reason it is doing this, the reason why it would fail is because we have a tuple and we are making 2 mutable references to it. First and second have mutable references. Right. First dot push underscore string SND. second, and second clear. Okay, so push string. What does push string do again? To be honest, what does it do? What even does that do to be? Does that? I thought push string would push. Does that push to the string? I believe it does. Yeah, that just pushes to the string. It doesn't like create a new tuple. And then second clear. Right, so we create a new string here, and then we clear out the second. So we add in second to the first, and then clear out the second. I don't see anything that can cause an issue here. I don't see anything that can cause an issue here. I really don't. Am I an idiot? I feel like there should be something which causes an issue here, especially if it's stating it doesn't compile. Right, let's go to the standard docs and read push string. Push str. Appends a given string slice to the end of the string. Yep. So this just takes, like, if this was hello and world, space world, this would make hello, hello, space world. And it would clear the second one, so that would be nothing. So if we have nothing here, and secondarily world, it would work. If we have world and secondarily nothing here, it would probably work. And when we clear the second... Wait, is this one of those weird secondary free things? Where it frees twice? Oh, okay. Right, so in order, it would free... Right, second is cleared. So it'll try and free second again. This is a double free. I think this is a double free. You have let second, which will eventually be freed at the end of this, unwritten, unseen. It will drop it. But it's already been dropped, so perhaps it won't. But it will drop strings. It will drop strings, which has the second string. Yeah. I think that's what it is. Thank you, Silver. I think that's... Thank you for the confidence. Yeah, I think that's correct. It's a double free. Right. I got 3 of the 7 correct. That's sad. That's very sad. Right, so that is correct. This is correct. I'm surprised. Okay, so we did get this one correct. That one took us a while. That one took us quite a while to get. But we did get this correct. Question 3 we probably got wrong. Let@me uses unsafe code to disable the borrow checker from checking the safety of mutable references. Okay. That's my answer, but that's not correct. Question 4 was incorrect. Question 5 was correct. Question 6 could not. Yes, so it was the other unsafe one. Right, so I'm just going to go in and get the answers so that we can see why, because I don't believe I could understand it correctly myself. Right, so let's read this one's context, because I'm quite curious on this. For haystack, the slice type reference string, that's a slice type, cannot accept more input than reference vec string, so it is preferred. For needle, the target substring does not need to be heap allocated. That's the reason? Yeah, okay, fair. So, string is preferred to string. For the return type, vector string is not desirable because it would require cloning the input string. Reference string is not desirable because it can only return a contiguous subset of the input. Vector reference string is the most preferable because it only incurs the cost of allocating the vector, not the strings themselves. Yeah? Okay, that makes sense. So the reason why this is preferred is because it does reference back to the original strings, and it only allocates the vector, saving us space and time. Needle being an at string is preferred because it allocates it within the stack. It's perfectly okay if string dies at the end of this. We're not going to use it. When the frame's done, it's done. This is preferred because it can accept more inputs than a reference vector string. So it is preferable. Okay. This one is wrong because SplitUp uses unsafe code to circumvent the borrow checker with raw pointers. Okay, so it is the raw pointer thing. Quite a few people do like it raw, so I can understand that Rust does this. Yeah, fair enough. SplitUp uses unsafe code to disable the borrow checker from checking the safety of mutable references versus just using raw pointers. Okay. Here is a bit more of an explanation if you want it. I might read that myself later. Reread that later. 4. We got this one wrong, really wrong. We said ownership permits borrowing and reborrowing. The reference s_ref can cause a double free. So it is a double free error. We did get that one correct. But ownership permits moving, and moving out of a reference can cause a double free. The ownership permission represents ownership of an object. There can only exist one owner of an object. Yes, so I guess when I said that s_ref owns it, not reference s_ref, I was correct there, but not for the exact reason. But I still didn't get the reason correct, so embarrassing. So it is important that references cannot transfer ownership of non-copyable types like string. If two variables thought they owned the same string, then they would both attempt to deallocate it, causing a double free. Okay, so it is a double free error here, of course. Okay, so if two things own something, both things need to free it, so... Yeah, okay, so ownership is more so what frees it. It's like, what has the responsibility to delete the object? Or sorry, the thing. Don't use object because of object-oriented programming. Okay, that makes sense to me. I think that's quite understandable. Understanding ownership as simply who is responsible for killing it. Question 5, I was correct. Well, I'm glad for that. The borrow checker will always reject programs with undefined behavior. I don't believe that. I think that that's a bit of a lie. But may sometimes reject programs with undefined behavior. Correct. This could cause undefined behavior. How? It causes a double free on any input. Does it? Yeah, it does. Yeah, it does. So we were correct about the reasoning for this one, but not this one. Apparently this is fine. This is perfectly fine and no double free exists. Well, you say it was obvious, but I'm never going to get that. Ever. I'm never going to get that. Period. We eventually thought of thinking about that in this question, but we didn't think of thinking about that in this question at all. And we were wrong when we thought about it. So it proves to me, at the very least, I don't understand this double free behavior, which is a bad thing, but I'm very glad that I'm learning Rust, because it'll tell me that I'm doing something incredibly dumb like this. Because it frees it once, and then frees it again. That it does. It'll free B2, and then it'll free B, which are the same thing. That is fantastic. Okay. Again, glad I'm using Rust because I'd fuck that up in C. Or something else that doesn't do this. Though I guess it wouldn't behave like that in C, or something else that doesn't work like this. But still. I'm assuming Rust would have a very good explanation of why in the compiler. Alright. This could not cause undefined behavior. The borrow checker rejects this function because it assumes that get underscore first and get underscore second could return a mutable reference to either component of the tuple. That's why, because we don't state which one of these we are returning. Could be either. That's why we went over that. We did. But the reasoning here, to bash it into my brain, is that we could return this, but we could also return this. And if we return this twice, we have two references to the same thing, which could cause, well, that's two references to the same thing. Two things can change it. I'm glad that we went through this because that makes sense. But we didn't in this case. It did also state later that the borrow checker may eventually allow this, if it can go through and check what everything is doing. Alright. So we finished this chapter. Completely. Finally, we are gone with ownership. Ownership no longer owns us. That is good to hear. That was one heavy-ass chapter. Honestly, I'm surprised we didn't die during it. How do you guys like it? Do you guys think that the idea of ownership is a good one? Do you think that ownership makes sense? Do you guys love it? Do you guys hate it? I personally love it. I like it a lot because I fuck up a lot, and as just a principle. Break things and break things quickly. Fail and fail quickly. That is my, that's what I try and do. I like it. You're coming around, but you need more time with it to love it. I completely agree. You might switch ideas later on. I might hate it. You might love it later. Yeah. I'd love to start coding with this, though. I really wish that this had just, like, small projects, but I want to start coding with something that needs... I believe that you, was it you, Silver Sorbet, that had given me... I can't remember what it was. The Rust by example thing? There's a Rust by example thing, like a Rust by projects. Rustlings! Thank you. I have a bookmark somewhere. Yeah, Rustlings. That's something I really need to go over. That's something I really need to learn this. That's where I'll figure out if I love it or if I hate it completely. Right, anyway, we are going to check up with the next chapter. But I have to go to a place where I must exhaust liquids from my body. I'll see you guys soon, but after which we are going to go into structs. Using structs to structure related data. I will see you guys soon. Hello! Welcome back, everybody! I hope you enjoyed your very short break. I'm talking in order to ensure that I am actually here again. There we go. Alright, I am back. I'm gonna wait a bit, because I'm gonna drink some tea. I believe that we are still here. Alright, I think that somebody may have left. Misunderstanding. That's reasonable. I did kinda say goodbye. If anyone's still here, I'd love to hear you sound off. Sorry to keep making you do... I don't know if you guys heard that. That sounded like the collapse of an entire kitchen. I think they're okay. No, I'm terrible at goodbyes, especially due to the fact that I'm going to continue. Yeah, it's like that guy who says goodbye and then stays for another 2 hours at your home while you're cleaning. Doesn't help out, you know? But anyway, I'm going to continue. Okay, using structs to structure related data. A struct or structure is a custom data type that lets you package together and name multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. We'll demonstrate how to define and instantiate structs. We'll discuss how to define associated functions, especially the kind of associated functions called methods, to specify behavior associated with a struct type. After we know structs, we can pretend we're doing Rust when in fact we're doing Java. Fantastic. Structs and enums, discussed in Chapter 6, are the building blocks for creating new types in your program's domain to take full advantage of Rust compile time type checking. Right. We're only going to go through this a bit. We have about half an hour left. Structs are similar to tuples. Defining and instantiating structs. Structs are similar to tuples, discussed in tuple type section. The tuple type section. What's that section? Is that... that's later on. Thank you for that. In that... Oh, no, that's way before. Yeah, that's just describing what a tuple is. Reasonable. Structs are similar to tuples, discussed in the tuple type section, in that both hold multiple related values. Like tuples, the pieces of a struct can be different types. Unlike with tuples, in a struct, you'll name each piece of the data so it's clear what the values mean. Adding these names mean that a struct is more flexible than a tuple. You don't have to rely on the order of the data to specify or access the values of an instance. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should be descriptive and should describe the significance of each piece of the data being grouped together. Then, inside curly braces, we define the names and types of the pieces of data, which we call fields. For example, listing 5-1 shows a struct that stores information about a user account. We have user, which is a bool, or active, username, which is a string, an email, which is a string, and sign-in count, which is an unsigned 64-bit integer. To use a struct, after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct, and then add curly brackets containing key value pairs, where the keys are the name of the fields and the values are the data we want to store in those fields. We don't have to specify the names in the same order in which we declare them in the struct. In other words, the struct definition is like a general definition for the type, and instances fill in that template with particular data to create values of the type. For example, we can declare a particular user as shown in the following. We have a user equals the user, email equals the email, username equals the username, this is a string from, active is true, and sign-on counts equals 1. We have inside the stack, which is, let's just look at this. This is not useful. We have stack, which is the main, user1 is a user with active. Yeah, okay, so username and email, since they are strings, they will be in the heap. Reasonable. These are just pointers to the strings in the heap. Alright. To get a specific value from a struct, we use dot notation. For example, to access this user's email address, we use user1 dot email. If the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. Listing 5-3 shows how to change the value in an email field of a mutable user interface instance. Function main let mute user1 equal user. We have the user. User1.email equals string from here. We can change it. Right, at location 1 we have this. We have user.email pointing to the email. Here we've changed it. Congrats. Note that the entire instance must be mutable. Yep, the entire thing must be mutable. You can't say that each individual piece can be immutable or... Right, so knowing a bit about another language called C, creating a string that is that long, and then adding in another much longer string should mean that we have to destroy the entire mutable instance in order to make this. Or, well, that's just a pointer. Fair enough, that's just a pointer to a string, so we can destroy the original string and add in a new string and then point to it, so that's fine. Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. As with any expression, we can construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. Is that returning? No, that's not returning. We can construct a new instance of the structure as the last expression in the function body. Okay, so this will return the user. Fair. I wish it would be so easy to just put the word return there, but they hate us. They hate us a lot. Alright. Listing 5-4 shows a build_user function that returns a user instance with a given email and username. The active field gets the value of true, and then sign-in counts gets a value of 1. Right, we create the user, and then we return the user from build user. Yep, it makes sense to name the function parameters with the same name as the struct field of the struct fields, but having to repeat the email and username fields, names, and variables is a bit tedious. If the struct had more fields, repeating each name would get even more annoying. Luckily, there's a convenient shorthand. Oh, okay, so if it's named the same thing, we can just put it here, and it'll take the value from... Is that any previous variable, or is that simply variables within the variables we pass in the parameters? Because the parameter names and the struct fields names are exactly the same in listing 5.4, we can also use the field init shorthand syntax to rewrite build_user, so it behaves exactly the same, but we don't have the repetition of user name and email as shown in 5.5. Here we go. So we got username and email, which are just these, but we don't have to do equals username or equals email. Right. Here we've created a new instance of the user struct, which has a field named email. We want to set the email field's value, the value in email parameter, in the email parameter of the build user function. Because the email field and the email parameter have the same name, we only need to write email rather than email:\email. Reasonable. Creating instances from other instances with struct update syntax. It's often useful to create a new instance of a struct that includes most of the values from another instance, but changes some. You can do this using struct update syntax. First, in listing 5-6, we show how to create a new user instance in user2 regularly, without the update syntax. We set a value for email, but otherwise use the same values from user1 that we created in listing 5.2. We have a snippet, user2 equals user. We have this, user1.active, user1.username, string from that, sign and count. Yep, reasonable. So, okay, we can no longer use user1. User1 is kinda dead. We've killed him. We just we have a pointer to the original user. Right. So when we do this, user1.active, we are by reference. We are making this by reference. So active will equal true. I guess, yeah, because this has copy. This has copy, so user1.active will just be true. That is not pointing to anything. That's just the value of true. But username and email, because they are strings, will simply be pointers to the heap data here. It will not copy, which is not a great thing. So user1 will be dead, user2 will be active. Because of this behavior, we are borrowing. The user1 no longer has ownership over its data. User2 does. Or user2.username has ownership over user1.username. Using struct update syntax, we can achieve the same effect with less code, as shown in listing 5-7. The syntax ... specifies that the remaining fields are not explicitly set. Specifies that the remaining fields not explicitly set should have the same value as the fields in the given instance. Okay, yeah, as you can see here, no, you can't see here. It's going to show us here. So we just want to change the email. The rest of it, we're just going to take from user1. Good. The code in listing 5-7 also creates an instance in user2 that has a different value for email, but has the same value for username active and sign and count field from user1. The ... user1 must come last to specify that any remaining fields should get their values from the corresponding fields in user1. But we can choose to specify values for as many fields as we want in any order, regardless of the order of the fields in the struct's definition. Good to hear. Note that the struct update syntax uses equal, like an assignment. This is because it moves the data. Just as we saw in the what is ownership section. Sorry, that was terribly said. This is because it moves the data. Just as we saw in the what is ownership section. This is because we can no longer use user1 after creating user2, because the string and username field of user1 was moved to user2. If we had given user2 new string values for both email and username, and thus only used the active and sign-in count values from user1, then user1 would still be valid after creating user2. So it is literally only because we are moving username and email, the ownership, over. That is the only reason. Okay, so that's kind of confusing because user1 is not always dead if we use values. It's only dead if we use values that do not implement the copy attribute. Okay. The types of active and sign-in count are types that implement the copy trait, as I had stated. So the behavior we discussed in copying versus moving out of a collection section would apply. Makes sense. Using tuple structs without named fields create different types. Rust also supports structs that look similar to tuples, called tuple structs. Tuple structs have the added meaning the struct name provides, but don't have names associated with their fields. Rather, they just have the types of the field. Tuple structs are useful when you want to give the whole tuple a name and make the tuple a different type from other tuples. And when naming each field, as in a regular struct, would be too verbose or redundant. Yeah, we have color, which is just 3 I32s. And point, which is just 3 I32s. We don't have to name X, Y, and Z. They're always going to be in that order. Makes sense. We don't really need X, Y, and Z to be named. Note that the black and origin values are different types because they're instances of different tuple structs. Each struct... So... Yes, of course. Right, I don't know why that sent me for a little bit. Again, very tired. Each struct you define has its own type, even though the fields within the struct might have the same types. So even though these are essentially the same thing, since it has a different name, you cannot put a color into a point, which would make no sense to do anyway. Each struct you find has its own type. Yep. For example, a function that takes a parameter of type color cannot take a point as an argument, even though both types are made up of 3 I32 values. Otherwise, tuple struct instances are similar to tuples in that you can destructure them into their individual pieces, and you can use a dot followed by the index to access an individual value. Unit-like structs without any fields. You can also define structs that don't have any fields. These are called unit-like structs because they behave similar to brackets, the unit type that we mentioned in the tuple type section. Unit-like structs can be useful when you need to implement a trait on some type, but don't have any data that you want to store in the type itself. We'll discuss traits in Chapter 10. Here's an example of declaring and instantiating a unit struct named always equal. Struct always equal. Function main. Let subject equal always equal. Right, so this would be useful for like flags and stuff. So if you pass that into a function and you don't want so if you pass it into a function, terrible at explaining this. It'll probably explain it better later. Apologies, but it's good as a flag. Always equal makes sense. That's just a bunch of words instead of having like different modes on a function being 0, 1, 2, 3, 4. It would be always equal, always false, sometimes equal, or only returns blank. Makes sense. To define always equal, we use the struct keyword, the name we want, and then a semicolon. No need for curly braces or parentheses. Then, we can get an instance of always equal in the subject variable in a similar way, using the name we defined without any curly brackets or parentheses. Imagine that later we'll implement behavior for this type, such that every instance of always equal is always equal to every instance of any other type. Perhaps to have a known result for testing purposes. We wouldn't need any data to implement that behavior. You'll see in Chapter 10 how to define traits and implement them on a type, including unit-like structs. Okay, that's strange. So always equal, if you're like 72 equals always equal would be true no matter what. Alright, I can see why that's useful for testing. In the user struct definition in listing 5-1, we use the owned string type rather than the slice string type. This is a deliberate choice because we want each instance of this struct to own all of its data, for that data to be valid for as long as the entire struct is valid. Makes sense. It's also possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature we'll discuss much later on. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. let's say you try and store a reference in a struct without specifying lifetime, like the following. This won't work. We have a struct, active, bool, username, all that stuff. Right, yeah. So this will just error out with this error. Makes sense. So we have slices, which could be there for God knows how long. The compiler will complain that it needs lifetime specifiers. Expected a lifetime parameter. Help, consider introducing a named lifetime parameter. Then we have that again here. More information? Try this. In Chapter 10, we'll discuss how to fix these errors so you can store references in structs. But for now, we'll fix errors like these using own types like string instead of references like reference string. Okay. Borrowing fields of a struct. Similar to our discussion in different tuple fields, Rust's borrow checker will track ownership permissions at both the struct level and field level. For example, if we borrow a field x of a point structure, then both p and p.x temporarily lose their permissions, but not py. So we have point, which is a tuple, which is a struct x and y. We have p, which is a point of type x. Yep, right there. All right, let's read this. I don't think I fully understood what it's saying. Right, so both the struct and field level, for example, if we borrow a field x, we borrow x somewhere. Yep, we borrow x here. If we borrow a field x of a point struct, then both p and px temporarily lose their permissions, but not p.y. Okay, makes sense. Yeah, so we can't actually... Right, so if we have p, which is an instance of point, and then we borrow p.x immutably, so we can change p.x. We're allowed to change p.x, but we're not allowed to change p. We can't destroy it, we can't move it, because x still exists, and x might want to use p.x. And if it tries to, it could do a bunch of different terrible things. However, we can still use p.y because, well, it's perfectly fine to do that. Like, p.x cannot change p.y, so p.y can be changed. We can read that, we can change it, we can do anything we want with it. As a result, if we try to use p, well, p.x is mutably borrowed like this. We're trying to use p here, and point, reference p, it'll fail. Because it doesn't have ownership over it. It can't actually do anything with that. Yep, p loses ownership, read and write. Can't read it, can't write it, can't own it. But p.y still has read, write, and ownership? Read and write at the very least. Then the compiler will reject our program with the following error. Cannot borrow p as immutable, already borrowed as mutable. Does it say? Here's where the borrow occurs. Here's where the immutable borrow occurs. Here's where you use it. More generally, if you encounter an ownership error that involves a struct, you should consider which fields of your struct are supposed to be borrowed with which permissions. But be aware of the borrow checker's limitations, since Rust may sometimes assume more fields are borrowed than they actually are. I'm looping a bit randomly. I don't really know what you mean by looping. Fair enough, though, honestly. I'm sorry, man. I'm really sorry to hear that. I don't really know how to fix that at this point, sadly. Right, so I believe what I'm just going to do is I'm going to stop. If I'm looping randomly, we're quite close to the end. I really don't think that we can... No, it's not my fault, of course. Technology is a failure, and society should return back to the days of wood. But, yeah. I think at this point, though, I am going to stop. We have 15 minutes left. Not enough time to change the next thing. And, well, I guess we could do the quiz. Honestly, I'm quite tired, too. Same. But yeah, thank you for being here, Keith. You did. You did DM me on Mastodon. Alright. I'll talk to you someday tomorrow or the next day. Message you on Discord or something. We can get together, talk about this a bit further. go over what we've learned to see if both of us actually understand or if I'm just pretending. Right, so again, thank you for joining me, Keith. As I'm terrible with goodbyes, I guess I'm just going to do it quite quickly. Once more, I appreciate you coming, always do. I hope you have a good day. Talk to you at a later point, but I am going to stop at this time. Bye, Keith.